So thanks everyone for joining us, and it's really exciting to have to start this seminar. On behalf of my co-organizers, Kira and Gary, I would like to thank the overwhelming positive response we got from the community, all the speakers who agreed to talk, and future speakers. We are really looking forward to this series. For joining us. And all right, so first of all, I have to ask everyone, please mute yourself. All right, I can. It turns out that. All right, so Sami at Tahar, sorry for calling you out. You are speaking. You should mute yourself. I can't mute you. First of all, I have to ask everyone. All right. Please mute yourself. Okay. So the problem is that I have one computer in which I'm constantly admitting people one by one, thanks to this amazing technology. Once I'm done with that, then I can start muting people. But I don't have the power to mute, okay, and
he's muted now.
So he's muted. Okay, good. All right. So again, everyone, please mute yourself and stay muted during the talk, and by default. But we also want to make this interactive. So if you have questions, then you can ask questions on the chat or on YouTube, which my wonderful colleagues are monitoring, and they're gonna channel the questions. And if you are attending the meeting live, then you will be given the opportunity to ask your questions by either Gerge or Chiara or me, least likely me, because I'm trying to stay on the top of all this streaming business that I know so much about. All right. So those are the rules. And without further ado, I think I have to ask one of my co-chairs to give a short introduction to Chi, who is going to give the first talk.
Yes, exactly. So, well, thank you, Chava. Thanks everybody for being here. This is very exciting, and of course, there's many technical glitches that you're facing. We apologize for that. I guess we're going to sort this out as time passes, and we gain more and more expertise in this. But now, let's get technical, and let me introduce the first speaker of this wonderful seminar series, who is Chi Jin. So Chi does not have a very long CV, but it's a very impressive one for sure. He just graduated recently last year from UC Berkeley under the supervision of Mike Jordan, and has now started as an assistant professor in Princeton. Yeah, so he's been doing some fantastic work on the theoretical side of machine learning, in statistics and optimization, and he has ventured multiple times into reinforcement learning theory so far, where he has done, again, very, very impressive work. And well, this is one of the things that he's going to be telling us about how to address the exploration exploitation dilemma under linear function approximation in reinforcement learning. So without further ado, please welcome Chi.
Thanks a lot, and thanks Chava, Greg, and Sierra to invite me to this wonderful seminar, and also thanks for organizing this. I think this is very needy for the entire field. And so, as Greg introduced, I'm Chi Jin, and I just graduated from UC Berkeley. I'm now assistant professor at Princeton University. So today I will talk about the proof of efficient reinforcement learning with linear function approximation. This is a joint work with Zhuoran Yang, Zhaoran Wang, and my Jordan. So first slide gives to the picture of my wonderful collaborators, Zhuoran Yang, who is at Princeton University, and he will be on job market next year, and Zhaoran Wang is in Northwestern University. I guess everybody knows my advisor, Michael Jordan at UC Berkeley. Okay, so This talk will come to have 3 parts. The first, I will do a little bit long overview, and then we'll come into a little bit technical details on the formal results we're stating, and then we talk a little bit about techniques, and finally we'll do the conclusion. Okay, so first, I guess since this is a first talk, we'll say a little bit more about what's reinforcement learning. Reinforcement learning has been heavily used in the applications called sequential decision making. Essentially, for any real problem, you want to make a series of decisions, and you have some interaction between the agent and the environment. Then reinforcement learning is the framework for you to use, and has been applied to robotics, to games, to art, to Go, and to a lot of different problems. And there are many very famous algorithms we use to solve reinforcement learning, such as value iteration, Q-learning, and policy gradient. To be more specific about reinforcement learning, we usually talk in theory about the Markov decision process. It has several components like states, action, and in this talk we talk about episodic Markov decision process. So we say each game has a finite horizon. It always ends in H steps, and it has transition and rewards. Let's just take this chess game as an example, and we have state here is more or less the position of each piece of each piece, the position of each piece. And the action is how you want to move each piece, like you want to move this pawn, you want to move the knight, or like move to the next position. Okay, and agent is basically you. And the environment, suppose you are playing with against a fixed opponent, like the opponent is always playing a fixed strategy, then the opponent is your environment. You are playing an action, and you go to the environment, and the environment will give you a reward and transition to the next stage, i.e. like to the next position. And eventually in this problem, the reward is just if I win the game, I get reward 1, and if I lose the game, I get reward 0. And the target of reinforcement learning is we want to find the best policy that maximizes the cumulative rewards. That is, in the long run, I want to find a way to play this chess. I can like win as many times as possible. So this is a non-rigorous way of saying what is reinforcement learning. And today's talk, we will focus on not only just about reinforcement learning, we want to do provable reinforcement learning, because we want to do reinforcement learning theory, and specifically want to do provable efficient reinforcement learning algorithm. Okay. And also we want to work this algorithm in a function approximation setting. So there are 2 keywords here. And if you don't know them, don't worry right now. And one is provably efficient. We will say just in a second, what do we mean by provably efficient? And the second one is what do we mean by function approximation setting? So we mean by provably efficient, we first want to say what is efficient. So there are 2 efficiency which is really important in practice. One is about sample efficiency. That is in practice for a lot of problems. For example, if you want to do autonomous drive, or if you want to train some robots, collect those samples can be really expensive. It can be either costing a lot of money, because if you want to do autonomous drive, if you crash your car, it costs a huge amount of dollars to just fix it. And it could also cost a lot of time. Like for example, if you want to do experiments for robotics, it takes like 5 to 10 minutes to just fold 1 tile and just do 1 experiment. And if you want to do thousands, 10,000 of experiments, it's going to cost a very, very long time. And second one is also computational efficiency. That is like the CPU and GPU is not like have infinite computational power. So in the modern days, if you want to train a deep IO system, it usually costs weeks, and some large systems even cost months. So we really want to have some algorithm which are both sample efficient and computation efficient. So this comes to the definition of the provable efficient algorithms. Basically, it says we want the algorithm that is will provably find a near optimal policy, that is the goal of reinforcement learning, with a small amount of samples and runtime. That is, we want to be efficient in both sample and computation. Okay. And the second part is about function approximation. To introduce function approximation, we first need to know what is on the opposite side of function approximation. So this is what we have been studying in the classical literature of reinforcement learning. That is called tabular IO. Tabular IO usually refers to those problems where we have a small number of states and actions. Like in this chess game, number of states is reasonably small, and number of actions is quite small. And it's called tabular because in those cases, we can, usually in the reinforcement learning, we define a concept called a value function. Value function here, like QSA, is usually defined as expected cumulative rewards if I follow in some policy pi and starting from this state as an action. So this value function, because the number of states and actions is very small, now I can represent this value function as an entire table, which the row is S, column is A, and the entry is essentially the value of this value function. So this is called tabular reinforcement learning. In the tabular reinforcement learning, we have a reasonably good understanding in theory, especially we know when paired with upper confidence bound, some exploration strategies, like classical algorithms such as value iteration or Q-learning is able to find epsilon optimal policy in this polynomial number of samples, which is a polynomial number of, in terms of H is the length of each episode, like the length of the game, and S is number of states. A is number of action, while epsilon is epsilon optimal policy. So the most important thing here is in tabular reinforcement learning, we say we need to pay some sample that is linear in S and linear in A. That is linear in the number of states. Okay. While when we move to the function approximation setting, or like in practice, what we observe is the number of states is really gigantic, enormous. Like let's take one entire game as an example. For example, this one. Like each states now become like each value of pixels, and we have like hundreds of pixels, and each pixel can take, for example, 10 values in terms of color, different color and different strengths. So easily it will be more than 10 to the 100 number of states. If we paying something as a tabular reinforcement learning, like we want some linear in terms of states, number of samples, it's almost impractical. We're never gonna get 10 to the 100 number of samples. So this is why function approximation is quite different from the standard tabular reinforcement learning. Essentially, we face the difficulty that most states are not visited even once. So just because there's way more number of states than number of samples we can afford. So we essentially need a new mechanism to solve this problem. We want the mechanism so that we can generalize knowledge from the visited states we have seen so far to the unvisited states, where there's most states we never been visited. It's kind of like also we want some mechanism to measure the similarity between states. Okay. So typically we do this by using function approximation. So-called function approximation is we know in the tabular reinforcement learning, this value function QSA or any policy is kind of like can be represented as a big table. And now we cannot do it as a table just because the number of states is huge. And if we want to write out this table, it's like gigantic table. We want to approximate this value function or policy by some pair function in most case, by some function f in a function class. And probably this class is like linear function, quadratic function, or some neural networks. So they're not that crazily complicated. They're not like they're not every function, but they're like a finite class of functions so that we can control the complexity within this function class. And this function class also implicitly encode the similarity between different states, or implicitly encode like how we want to generalize knowledge from some states to some other states. It turns out those function approximation setting is much more challenging than the tabular reinforcement learning setting. And just remember, in tabular reinforcement learning setting, we roughly have pretty good results under no very strong assumptions. However, the existing theory for function approximation is quite different. So one class of results we have been so far is similar to like fitted Q iteration, which is by Chaba and Remimuno in 2005 and Chen and Zhang in 2019. Usually this line of results is kind of, for example, but there are also a lot of other algorithms. Those algorithms usually assume in some form we have access to some representative data, either by like assuming we have generated a model, that is we can go to any states freely, or we kind of have access to some data where data SA is generated from some distribution mu, so that the mu have this very good property like the ratio between the probability of visiting state A as A under any policy over this mu is upper bounded by some C. This is just one example. If you don't understand this concept, don't worry. But basically what I'm saying is you assume you have some data which you can for free visit all states or like all representative states in some sense. So the most important problem about here is that there's no exploration mechanism encoded in this line of theoretical results. And we will say a little bit later what's exploration and why it's very important to reinforcement learning. The other one is more generic. It actually deals with exploration, such as those like Bellman rank and Olive by Zhang et al. In 2017. And those are generic results. And those are saying as long as some condition like Bellman rank is small, and I can do exploration, I can solve this like function approximation problem. But the problem is they don't have the computational efficiency, and they're in fact computational inefficient. So this leads to the key question we want to deal with in this talk. Can we design provably efficient algorithm without those like data representative assumptions? That is, we want to deal with this exploration versus exploitation trade-off. And also we want to do efficient, so we must have sample efficient and runtime efficient. So this talk will say, yes, we can do it, but we don't do it for like generic function approximation. We can do it for a subclass that is called linear function approximation. Okay, and what is linear function approximation? That is, we just consider a linear function class. In this talk, I will always say I want to approximate the value function with I want to do approximate the value function by some like function class. In this case, a linear function. So this value function QSA would be linear in terms of underlying feature map phi of SA, and we have some weights W, where W is in some constraint set and W is in D dimension. And overall, this across this talk, I will always assume the feature map phi is null. So this is really just we want to solve this W, which is like what is this linear function? Linear function approximation, although sounds like a little bit simple compared to like deep neural network, for example, but it is in fact like pretty frequently used in practice. Before the rise of deep reinforcement learning, I think most practical problems usually use linear function approximation as a baseline. And even nowadays, like some problem like Tetris or some other problem, like you can design very good features and then just use linear function approximation, you will get pretty good performance for those applications. And in this work, specifically, we will consider a linear MDP model, we will say later. And this linear MDP model will say, as long as we do linear function approximation, this function approximation is kind of good enough. So this is saying the transition and the reward is linear, and that's called linear MDP. And we will also use a very classical algorithm in the linear function approximation IO literature that's called least square value iteration. It is just a well-known value iteration, but use it in the least squares way. The next thing we say a lot is we need to deal with this exploration mechanism. What is essentially about exploration in reinforcement learning? That is, like for example, if suppose we have already seen a lot of states in action, and one way to exploit.
Sorry, we lost your screen. Can you share again?
Oh, what? Where?
Yeah, can you again press present now in the Google Hangout?
Let me just stop sharing and sharing. Is that good? Is that good?
Yes, yes.
Okay. Yeah, please let me know if this goes wrong. Okay, so we talk about exploration. Suppose we already visited a lot of states in action, and one way to exploit our current knowledge is we just basically say, I already know those states in action. I will try the best strategy, like based on what I know so far. But what we haven't done is there might be some other states we have never visited before, and those states may lead to much better rewards. So in terms of exploration, yes, we want to try some other actions or try some random actions with something we haven't tried before, so that might lead to some better states and leads to some unknown scenario we have never experienced before, and that might be better. So in like a classical way, a lot of people would say, okay, we want to do exploration. Why not just do epsilon greedy, which is one of the very simple algorithms to do exploration. That is, with a majority probability, I will take greedy action, take greedy respect to what I know so far. And with some small probability epsilon, I will do some random action. So this random action, although probability is small, it will lead me to try some other action and eventually give me some probability to try all the states. Okay. Unfortunately, in RL, exploration problem is more challenging than the classical bandit setting. People may know, especially like this epsilon greedy algorithm or like a random exploration algorithm would require 2 to the h number of samples in the worst case. That is, if a game like Markov decision process is have h step in total, then the number of samples would be exponential in the length of this game in the worst case. So this is why we need to take a lot more care about the exploration algorithm we're using. And it turns out in the bandit literature, there is a much better exploration strategy that's called upper confidence bounds. And we can use this upper confidence bound strategy, UCB, also in this reinforcement learning setting. And this gives us roughly the ingredient of our results. I will just briefly mention here. We consider the setting of a linear MDP, where linear function approximation is already sufficient, like doing a very good approximation. And we use a classical algorithm called least square value iteration with this UCB exploration. Okay, this is basically just our algorithm. And we prove this algorithm is able to find epsilon optimal strategy, epsilon optimal policy within this number of episodes. dq h to the 4th over epsilon squared. Here, h is the length of episodes. It's the same thing because we look at episodic reinforcement learning, and d is dimensionality of the feature. We note very importantly in this theorem, we don't assume any data representative assumption. So we're not like assuming we're given some very, very good data which already explore all the states. We actually collect the data by ourselves. And the other very important thing we note is this only has like polynomial dependence on dimensionality instead of any dependence on states and action. So this is very different from tablet reinforcement learning, which scale linear in terms of number of states. Now we have some polynomial dependence in dimensionality, but no dependence on states and action. So what it says about this result is, I believe this is like the first provable efficient algorithm for linear function approximation. So we have two keywords. One is provable efficient. The other one is a linear function approximation. And we mean provable efficient means we have polynomial number of samples and polynomial runtime.
Chi had a question in the chat, which is, do you still assume that the number of states is finite?
No, we don't need to assume that. Number of states can be infinite.
I see, thank you.
And this O tilde had some logarithmic dependence on D, H, and epsilon, but not on S and A.
Yes,
there's no dependence.
There is a follow-up question, which is that whether the number of state needs to be countable.
No, there's nothing like that. It can be like continuous states. Actually, the results only depends on the feature map is like in Euclidean dimension, Euclidean space RD, and state space can be anything. We don't very depend on that. Okay, so this concludes the overview of our work, and if there's no further question, I will continue to talk about the formal results.
Oh. Wait, so there is actually a bunch of questions. So one question that was asked, you mentioned at the start that most states are not visited even once, and to generalize knowledge from visited to unvisited states, use functional approximation. My question is it possible to change our view of states, like transform them so they could be less...
Change what? Sorry?
The view of our states, transform them so that they could be less in number and more visited?
I think it's yes, and there are some results. And there are actually a lot of work along this. I think this is more related to like state aggregation, like you kind of like you say some states are similar, and so you kind of like you group them as a mega states or something, and that's a little bit different approach than this
is it though different? Like, couldn't you do that with
yeah, I can also do that.
feature map, right?
Use
Like
feature map.
Yes. Piecewise constant feature map, which actually just models which states are aggregated.
Like, I kind of like encode those knowledge in terms of this feature map and map those similar states into the same feature map or some close feature map.
Sounds good. All right.
Okay, so let's talk about the formal results. So we first formally state what is episodic MDP we're talking about. And so as we just said, this S is set of states. So we don't really say anything about the cardinality of states. It can be infinite, it can be incountable. And we have this H is the binary horizon of the episodes. So the most important thing is we assume the game always stops in H step. Here we kind of take the last action H, and XH plus 1 is always some dummy states, which kind of like we don't receive any rewards after that. The transition probability is from any state action to the next states, and the reward is a map from state action to 0 to 1. And the way we kind of like we collect data or we interact with episodic MDP is we always assume we have some fixed initial states. So in the paper, we can deal with some adversarial initial states, but for simplicity of this talk, we just always assume we have some fixed initial states. That is, we always start from one single state. An agent is only allowed to pick actions. That is, he start from the first state, and he allowed to pick the first action, and then he observed the rewards and transition to the next state, and then he picked the next action, and he observed the reward and transition to the third state, and so on and so on. This is basically the way you interact with MDP, and it's more difficult than those like those settings which we assume we have access to representative data, because for those scenarios we kind of like say the data already give me for free. I have some data for all states or for every representative states. But here, because we always assume from one single state is not like all states. So it's just one single state. So most of states I have never seen in the first step. So we need actually to pick a sequence of actions to guide us to the states we want. And how to pick those actions to guide us to those states we want is kind of like a non-trivial problem. So that's why we need to deal with exploration in this episodic MDP setting. Okay, and a few standard definition, like when we talk about policy, we always talk about map from state to action. That is when we see the first states here and how we pick the action. This is like deterministic policy. And the classical definition of value is the expected cumulative rewards starting at step H from some states. That is the V value function. And if we start from, instead of just a states, but start from a state action pair, it's a Q value function. The important thing is because we're in the episodic setting, so it matters what our value is, how many steps will remain. So this value will depend on which step is like in this MDP. So this is slightly different from infinite horizon setting. It depends on H, but they're more or less the same. And the objective in the reinforcement learning is we want to find the optimal policy so that we can maximize the value. So this should be V1 in the first step, V1 pi of S1. That is, we want to maximize the initial value of initial states, okay, and maximize this pi. Okay, so here comes the interesting part. So we mentioned we're actually assuming the linear MDP. So what is a linear MDP? Linear MDP is somehow like you can think of something as we kind of like take analog of bandit literature, where moving beyond from multi-arm bandit literature, you want to say the linear bandit. So in this case, we call it linear bandit, which is assumed the reward is linear. So in this case, in MDP, we have not only reward, but also transition. So one simple thing we can directly think is why not just assume both transition and reward are linear. So in terms of linear reward, we mean this reward function is something linear in this feature map, phi SA, and some weights c theta h. So the most important thing is reward is linear in this feature map, phi SA. And the second part is the linear transition. This actually is not some assumption we come up with. It has been like done by a lot of previous work. So what I assume is the transition is the conditional measure of condition on current state and action. What's the measure of next states? And we say this measure is actually a linear inner product of, it's linear in this feature map psi, and some mu, measure mu. Okay, and this mu actually is a d-dimensional measure. What do I mean is each dimension is a measure. So it's a vector of d different measure. And so this inner product will give me a measure, and this will give me a probability map measure of conditional distribution of next states, conditional state, and action. Okay. So in the end of this talk, we will discuss some relaxation of this linear transitions. But so far, let's just stick with this linear reward and linear transitions. First, because we introduced the linear MDP, we need to say what is some example of linear MDP. Is it an empty set, or it actually is like a reasonable? So the first thing we would like to say is tabular MDP. It is a special case of linear MDP. To see it, we can easily just make the dimensionality to be number of states and action, because this is tabular MDP, so number of states and action are pretty small. And then we can make this feature map from SA to be the basis value vector, because we have SA different dimensions. So we just map each state action pair to its basis value vector. Then in order to specify the linear MDP, we only need to specify what is each coordinate of this reward weights and also this transition weights. We just make this theta vector, each dimension of the theta vector, to be exactly the RHSA in the tabular MDP, and each dimension of this measure to be the transition probability in the tabular MDP. Then we just essentially instantiate the tabular MDP as a linear MDP. Okay, and definitely we can have some other sets which is slightly beyond the tabular MDP, which is we consider feature space not necessarily just in the basis vector. We can be anything that is in the d-dimensional simplex, as long as like each coordinate summation equal to 1. And then we let this d-dimensional measure, each coordinate, to be any probability measure. This will also well define an MDP. That's a linear MDP, but that's something slightly more general than tabular MDP. But I also want to comment out, this linear MDP is definitely some result in the progress, and I don't think it's like any result. It doesn't include a lot of interesting models. So we will also comment about this point in the very end. So the very important property about this linear MDP is the following proposition, which is the most important property we need to use. In the linear MDP, because the reward and the transition are linear, then we can prove for any policy pi, the value of that policy is actually linear in this feature map psi SA for any policy pi. This is very important. Therefore, we can say the linear function class is sufficient to model all the values for all policy, because all the values is just linear. So when we do the linear function class, it's definitely it's well specified. There's not even bias in this scenario. Okay. Then let's talk about if we're clear about the setting about linear MDP, then we talk about the algorithm we use. So what is a least square value iteration? To introduce this algorithm, we first start with a tabular setting. We talk about the value iteration. Usually when we talk about the value iteration, suppose we have some collection of data, which in terms of SA, S prime pair. SA is current states action, and S prime is the next states. The standard value iteration is we just do some Bellman optimality equation. That is, Q value is equal to the rewards of current step and the expectation of the value in the next step. When we do value iteration and we have data, instead of we know the exact expectation, we will do an empirical expectation. That is, we use empirical data to estimate this transition matrix and use that as like my estimate of my true transition matrix for my value iteration. So we can see this updates actually equivalent to solve this odd mean problem, where essentially you solve this square loss between your Q value and the current rewards and the next value of S prime. Okay, this is the odd mean. And when we move to the function approximation setting, what do we mean by least square value iteration is very simple. Because in the function approximation setting, this S is very large. And when we do this argmin, Q is kind of like a function of SA. If we don't put any constraint in this Q, this could be a very complicated function. And in the case like S go to infinity, number of states is infinity, then it's very difficult to represent what this argmin of Q is. So least square value iteration is essentially saying I restrict my representation power of this Q value to be a linear function of psi SA, of phi SA. Okay, and instead of minimizing over all possible function Q, I just minimize this over this linear ways. I minimize over linear functions. And I will use this linear product of this phi and the W as my Q value function. And this defines least square value iteration. Okay, and it's like pretty classical algorithm. So far we have been talking about least square value iteration, but there's one problem. That is, we assume we're given the data as A S prime. So when we solve the reinforcement learning, we're never given the data. We need to collect the data ourselves. So now the question is how to collect the data. As we already introduced in the overview, we're saying we will use some more sophisticated exploration strategy, not the epsilon greedy, but use the upper confidence bounds. So I will just briefly introduce what it means. And this kind of algorithm is introduced in the literature of multi-arm bandit, where in this case, suppose I just have two arms, two actions, action A, action B. And each time I take actions, I will receive some rewards. And the rewards is a kind of like a reward is a random rewards with mean mu1 and mu2. And in this scenario, I take action 1 for 4 times. I observe like this reward in this position, and I take action 2 for 2 times. I took this reward in this position. So for all case, I can have an empirical mean, and I can more or less estimate the standard deviation about what I observe. So I can construct a so-called upper confidence bounds. That is the estimated largest plausible rewards for each action. So because I only observed 4 samples, so I think for the first arm, maybe the mean reward will never be greater than this blue line. And the second one, because I only observed 2, I only take 2 times, so I'm much more uncertain. So I'm saying the mean reward will never be greater than this green line. And the UCB algorithm, or the way UCB algorithm, like to take action to collect data, is essentially just take the action with currently the largest upper confidence bounds. This is the way we do the algorithm. So now with the ingredient of LSVI, least square value iteration, and UCB, we come up with our algorithm. So this is the high-level meta algorithm we run in our paper. So for each episode, we kind of decompose into 2 big chunk of steps. The first step is we compute Q upper bar, which is an upper bound of the Q star H. Q star H is the value of the optimal policy. And we compute this upper bound by doing least square value iteration with some bonus for all steps. So basically the first step is just to compute the upper bounds. And this is, we know by least square value iteration, as long as you give me the data, I can do it. And now I'm just adding a little bit bonus. And second step is regarding how we collect the data. We collect the data always by executing the greedy policy regarding to this upper bound. So if we see the state SH, then we just look at the upper bounds, we compute Q bar and over all A, and I do argmax of A. And this will be the action I take for that steps. And this is the way I collect all the data. Okay. So this is the algorithm. So I will say a little bit more about how we construct this UCB, or like what's the upper bounds of this Q star. So our UCB form has 2 parts. As I said, the first part is a linear part, which is an exact solution of the least square value iteration. In the previous slides, we see it. And now, because we want to say it's not only just a mean estimate, it's an upper bound. So we need to estimate, we need to add a quadratic bonus here. Where quadratic bonus, this bonus is not linear, it's a quadratic in this psi, the feature map SA, which interpret with a matrix, this lambda H inverse. What this lambda H matrix, lambda H is a summation over T, of this phi ht inverse plus some linear regularization, where this phi ht is the feature map of the state action I observed in T's episodes, i.e. like in the previous episodes. So this lambda matrix is essentially the grand matrix of features in the early episodes. And we take inverse and we interpret in our direction. So why we're doing something like that, and this is actually something very similar to the linear binary community. They always do this kind of projective bonus, because we can say this projective bonus is roughly equal to 1 over n, where n is effective number of times we have seen phi in the direction of earlier data. Why we're saying that? Because this phi t is kind of like the earlier data, early feature map. If they're all like in some basis, then if we just look at each direction, then that's exactly how many times we have visited that direction. So now, because they're not in orthogonal basis, they're in some random, they're in different directions. So we will see effectively we have seen that many samples in that directions. And then we will do inverse, and we look at that direction, so that will become 1 over square root of that. So this is more or less the intuition why we want to do that kind of bonus in this scenario. And finally, this is a theorem you have already seen in the overview for linear MDP. Least square iteration with UCB will find the epsilon plus in this number of episodes. And it's independent of states, independent of action. So the main takeaway of this result is saying now we have a kind of a basic theory now for linear function approximation about the proof efficient algorithm. Okay, and this concludes the formal results. And if there's any question, no question.
Oh, wait! Like there's like hundreds of questions. Like the internet just blew up.
Okay.
So let me go one by one, and more questions are appearing. Sorry, guys. Like I noted like 8 so far, which are definitely worth asking. So one question. So this is great. Worst case result. Do you have any instance dependent bonds? You know, like the type that we have in bandits with inverse dependence on the gaps and whatnot.
We haven't got it in this paper, but for Tabor MDP, I think Max and Kevin has some nice results about instantiating those all previous worst case regret bound in terms of instance dependence. And for linear MDP, I think that kind of thing might be possible, but that definitely requires some more work. But I think it's something, some direction we should
right. I guess maybe the worry is that you could have an algorithm which is just min-max optimal, and it misses the opportunity to exploit additional easiness of the problem if that easiness would happen. So do you have any sense of whether the algorithm, this algorithm, is able to exploit easiness of the problem?
I think probably we need some small modification, but not a lot. It's kind of also similar intuition in the bandit literature that UCB is also instance optimal, while like EXP.
Is it though for the linear case? For the linear case, is UCB linear UCB instance? I don't think so.
Oh, I see. Linear case, linear case. I'm not fully sure about what do we mean by instance dependence.
We do have some
because
results about this.
It's also a little bit vague to define how we do it.
Yeah. I'm like, if you have finitely many actions and they have feature vectors fixed to them, then you can define gaps safely, and you will see that UCB is just can be a pretty bad algorithm in terms of like leaving a lot of reward on the table when it doesn't need to, because it eliminates actions that can give you a lot of information about arms that are near optimal, but it just eliminates those. Like, okay, so right. The inner structure is funny.
Definitely a lot of more things need to be taken care in the linear setting compared to the
I think that's a super cool and interesting problem.
Right.
Other question was misspecification. Do you have results for misspecification? How do they look like?
Paper, we actually have some a little bit weak results for misspecification. So in a sense, we assume this. So we talk about it's a linear MDP. That is, we have this linear transition. Right. So in our paper, we also say if we don't have exact linear transition, but we have some transition that is close to a linear transition in the TV sense, then we have results. That is, if the TV arrow is some zeta, then the regret will be linear in this zeta. So it's zeta t. So we always pay this bias, but as long as this zeta is small,
but it's guessed in a gradual fashion with the misspecification error.
Sorry, could you say it again?
So the scaling of the regret is like linear exactly with the misspecification level. That is like things don't blow up like suddenly when the conditions are not met.
They don't blow, sorry,
they don't blow up like rapidly when the conditions
are not.
No, they don't
blow up. Yeah. So we have proved that.
Right. So
but we say it's a little bit weak in the sense it's like TV distance. So it's
right. I mean, yeah. Okay. So a related question was, do you think that this linear MDP assumption is just like way too strong, or like what's your take on this? And the related question,
it is a little bit strong, but
wouldn't
we'll
like
talk about that later.
Oh, you will talk about that. Yeah, like a related question was whether maybe a generalized linear model would be more appropriate if you're talking about maybe transition probabilities, right? So
yeah, there's some follow-up work on generalized linear model as well.
Good. How about having many more actions, like the algorithm, has to enumerate the actions, maybe continuously many actions.
I think so. This goes back to the how you're gonna solve this greedy policy, like
right.
the argmax of A. So if you say my feature map has some specific form, so that the argmax can be solved efficiently, then it doesn't matter like how many actions you have. So the number of action will only come into play into our algorithm is only in this argmax step, the computational. So doing the argmax might depend on the kinetic of A or like specific form of the feature map. If you're saying I can solve this argmax always, then there's no dependence on A at all.
Yeah. Oh, by the way, so did you, like, maybe I missed the slide because I was trying to read the questions too. Did you have a slide about the overall computational complexity in terms of like if you have finitely many actions and you have D dimensions and
I
age?
Talk about it, but because it's kind of like in this algorithm, basically every episode I'm only doing some polynomial. I don't have slides, but basically just because in every episode I'm just doing some polynomial operations of state and actions. So it's just some. Oh no, sorry, polynomial of dimension, like a matrix vector inner product or something. So it will be just some sample complexity times a trivial factor of B, and in a sense, like we can do some priority queue or like heap to do this argmax.
Yeah, well, I guess the bonuses are not going to change very frequently or like rapidly, and the values are not going to change rapidly either. So you can probably amortize the computation.
Oh yes, it's kind of like classical techniques in the value creation or like in the band. Then like you don't need to update in every episode. So you can like wait.
So still speaking about the model, like what if like you had expanding feature dimension? I guess the related question: can you do this in RKG spaces?
I will also mention a little bit about the.
Okay.
Yeah. So why not let's just do the main techniques. I only have 10 minutes left.
Yeah, sure. Let's go.
It will be very fast. Yeah. So the main techniques, I just want to say a little bit about the main techniques. I think this is like more or less for experts who like know this kind of analysis. And clearly, like we need to use all the previous analysis in the tabular MDP about the value iteration and about upper confidence and how to adapt them into the reinforcement learning scenario. So there's one key difference between this tabular reinforcement learning and the function approximation. We will actually say it here. Is about like when we do this value iteration, usually we say is that we kind of like, as we said, we already just apply this empirical transition matrix where this E hat is computed by doing average over all the data I observe. In tabular setting, it's just reweighting this, like a ratio of this counts, number of SAS prime over number of time I observe SA. And it's kind of like essentially I represent my empirical transform matrix as a multi-model distribution. However, in the linear setting, because we are also doing least square iteration, although it's not exactly the empirical transform matrix, but we have some equivalent version of that kind of thing. Okay. So this is, if we write out the least square iteration, this is essentially the formula we will have in this scenario in replace the empirical transform matrix. So what it says is, instead of saying I only look at the previous samples which exactly has the same state and action, I use that counts. Now, because it's a linear, it can be any direction. I will use all my previous features I have observed so far, but I will do a reweighted version. So we will inner product with this Gram matrix. If this inner product is very large, then I'm saying the transition information I get from that sample is heavily have a big impact on my estimate here. But if the direction is kind of like perpendicular or something has a very small inner product, then it has a very small impact on my current estimate. So it's kind of like a reweighted estimating of all the previous data we have observed. So this is like the next step we observe in these episodes, and this is ways how much it contributes to the estimation I have here. Okay, so this is what we call the empirical transform probability here. But you will note in the classical tabular setting, we need to use this empirical transform probability measure. It has a lot of good property. First, it is a well-defined probability measure. It's just a multi-normal distribution. Is of course it's a probability measure. It also has a monotonicity property. That is, if I have a two-value function, that for all the states, the first value function is smaller than the second value function, then applying this p hat, that is taking expectation over those states, will maintain the monotonicity. The p hat over v1 will always smaller or equal to p hat over v2. However, none of them is true for this p tilde. You can actually say the definition of p tilde, this weight can actually be negative. So you don't even guarantee each entry has to be a positive measure. So that sounds very bad, and that's also, it's kind of like also technical challenge and why the proof for tabular MDP not directly extending to the function approximation setting. However, in the linear MDP scenario, we have something very good instead. What we can say is for any value function in this form of linear part, which is done by least square iteration, and plus this quadratic bonus, essentially the upper bounds we use in our algorithm, then we have this concentration. That is this p tilde, some like a pseudo empirical transition matrix we have for least square iteration, minus the true empirical transition matrix. When you're taking expectation over all value function, this difference will be very small for all value in this class. And instead of saying p tilde don't have any nice property, we're saying the true transition matrix have very nice property. They have all the nice property p has. So we essentially, we kind of like, we say, instead of p tilde has any property, we say p has a property, and p tilde is pretty close to p. So the main mechanism here is that we use a uniform concentration. We're saying this uniform concentrated for all value functions. And this way has a pros and cons. The pros is basically now this approach has become much easier and much easier to generalize to other scenarios. But the cons is in the tabular setting, we don't heavily depend on this kind of uniform concentration, and it's not pretty clear whether there's such thing is really like necessary in the function approximation scenario.
Sorry, I got a question. So when you say uniform concentration, do you mean that this quantity is going to be small for every single state action pair, or just on every?
For every value function. For every value function, also for every state action pair.
Okay, but then how do you define this average? I thought it was conditional on the state action pair, or?
Not for every state action pair, but for state action pair introduced by the policy we play.
I see. So the ones that you actually visit,
yes,
and under these expiration bonuses, right?
Yes.
So not necessarily for the other states.
Not for other states, yeah. Because this is like an exploration setting. We don't necessarily get a visit of the state.
All right, perfect. Thank you.
Okay. And the final thing, technical thing, is we want to talk a little bit about relaxation of linear transition, which a lot of people ask. Just because in this paper, we assume the linear transition, and which is in a form like transition probability is linear in terms of this phi vector and also some other like a vector measure. And it turns out our proof can directly generalize to so-called optimistic closure assumption. This is also written out more in detail by some recent work in this paper. And what it says is we don't necessarily say this transition matrix has to be linear. All we need is when we take expectation condition on any state action of the value function, this expectation has to be linear in SA. And it has to be linear in SA for all the value function, which is in the form of a linear function plus the projective bonus, like in that form, like basically a linear function plus a square root of projective function. So if for any value function, we say the expectation itself is a linear, then our proof directly goes through. This is called optimistic closure because we assume for all optimistic value function, it is the expectation it will be a linear, close in the linear function. Okay, and of course this is still a reasonable strong assumption, and I think one limitation I feel like a little bit unsatisfactory about this kind of thing is when people study control problem, and there's one model which is very famous that's called LQR, linear quadratic regulator, and unfortunately LQR would not be included in this optimistic closure assumption. So our theory could not explain like how to do LQR. It's kind of like a little bit perpendicular to directions. So one could ask, could we relax this assumption to include LQR, which is still pretty open question. And some other people may even just wonder, because our linear MDP assumption essentially assumes for all policy pi, Q pi is a linear function. Would it be possible to just relax the assumption to just assume the Q star is linear? I think this would be probably too weak to be true. And there are a lot of evidence recently, like some paper by Sean Zhu, and also Chaba has a paper about it. And it's saying like, as long as you say Q star is linear and with a little bit of noise, then you suffer some hardness about doing that kind of thing. And if you only assume Q star is linear, which essentially you don't assume anything other than Q star like has any property, well, like in practice we observe some samples, a lot of times we won't be getting Q star, we will get some approximate version of Q star. So if we don't have any property for those value functions, then it's very difficult to do anything. So what I'm saying is basically this is like probably too weak, but there's still a lot of open space we can explore in the middle, and which we might get some positive results in those scenarios. Okay. And I will just very quickly conclude my talk. So this talk essentially just says now we have a provably efficient algorithm for approximation, and provably efficient in terms of we have point number samples and runtime. The algorithm is clean. It's just least square variation plus UCD, and a little bit like considerable part is we actually need to under linear MDP assumption, which there are a lot of space we can improve. The sample complexity is some O tilde dq H4 over epsilon squared. The most important thing is no longer depends on the number of states and number of actions. Some complexity only depends on the inherent complexity, that is dimensionality of the space. There are a few future directions we can talk about. One is relaxing this linear MDP assumption we just talked about. We hope we can incorporate the LQRs at some point so that we can have a unified story about this linear MDP of MDP on the linear function language. The other thing is we can also discuss the optimal sample complexity in this scenario. Like for now, we have D cubed. And the reason is we need to use uniform concentration. Is there any other techniques to get rid of that kind of thing and getting us some like linear dependence on dimensionality, which is like some focus, which a lot of people have been working on that for tabular setting, which you're getting very sharp dependence on S and A. And here we want to also have sharp dependence on like the function, the complexity of the function class. And finally is, of course, we want to do beyond linear function approximation, like kernels, RTSS and how to do that kind of thing. That's kind of future directions. And I would, this is like the reference I use in this paper. I would also just briefly mention there are also a bunch of work like by Linear Yang, Yang and Wang, and other authors. And they are slightly earlier. They're earlier than our work, or they're some of them are parallel. They also study this linear function approximation scenario, and they also pretty good. And there are some pros and cons on different assumptions and different algorithms used. And if you're interested to see, and you can also refer to our related work, see what's the difference between those works. And I guess that concludes my talk. Thank you all.
All right, thank you.
Awesome. All right, so just very quickly, if anyone wants to hang around a little bit more, we're gonna stay a little bit more. It's going to be off the record, so it's not going to be recorded or anything like that. Or it will be cut off after recording.